Siddhi, proceed.
Good evening, everyone. Welcome to the Centenary Celebration of Department of Mechanical Engineering, IIEST Shibpur. Before you, this is Siddhi Suman, a third year undergraduate student of this institute and host for today's evening. Today, we all are here for the 21st lecture under the Centenary Lecture series, which is to be delivered by our Honorable Alumnus, Dr. Pradip Saha, on the topic Nuclear Power and its Role in Carbon-Free Electricity Generation. This session will be chaired by our distinguished alumnus and constant supporter of this lecture series, Professor Kamal Sarkar, who is Associate Professor of Practice at University of Texas. I would like to invite Professor Kamal Sarkar, sir, for the further continuation of the program. Sir.
We're not getting the sound.
Please unmute.
Sorry. It is my great pleasure to introduce my friend Pradip, Dr. Pradip Saha. Going back in time, our beloved and illustrious Professor Amitavada, Professor Ghosh, had in my mind two most favorite students. One was Pradip, the other was Ashokda. Pradip was the topper in our time, 1968, and he got the gold medal during that time from all the departments in our college. Pradip is a very soft-spoken gentleman, perfect gentleman. He's very intelligent and hardworking. I have rarely seen a combination like him, combination of soft-spokenness, intelligence, and hard work. And if he says you something, you can take it to the bank. His journey started with the gold medal, but that was the first gold medal. Many more to come later. Following his focus in everything he does, he came to Georgia Tech and did his PhD under internationally acclaimed pioneer Professor Novak Zuber, who is well known for his two-phase flow. And following him, Pradeep did again the similar path, illustrious path, and he became internationally acclaimed in nuclear reactor, thermohydraulics, and safety areas. I'm not going to go to the laundry list of all his achievements, but rather touch upon a couple of few things. He is a very distinguished member of American Society of Mechanical Engineers and American Nuclear Society, and he is a fellow of both of them. He also has received Albert Nelson Marquis Lifetime Achievement Award in 2018. He worked in the internationally famed organizations like Brookhaven National Lab, MIT, GE, among others. Expectedly, he has lots of well-cited patents and papers, and he also authored a book called Nuclear Reactor Thermal Hydraulics, Past, Present, and Future, published by ASME in 2017. In between all these achievements, he also tried his hand in entrepreneurship, and he worked in India with his company called Protherm for almost 16 years. Now, going back to his achievements and accomplishments and his dedication to his field and his alma mater, I have requested him to come and join this forum. And I was telling in another forum that it is very hard for anybody to pack 50 years of experience, focused experience in 50 minutes. But Pradeep is awesome. I'm sure he'll do a wonderful job. And welcome, Pradeep, again. And the floor is yours. Please go ahead. Thank you. Pradeep, you can start.
Hear me?
Yeah, we can hear you.
Okay, so I can share my slides. Let's see what happens. Yeah, can you see? Okay, now full
Yes.
screen, right? Okay. I learned from my friends because you see, I am full screen mode. Yeah. Okay. Can you see?
Yes.
And you can hear me also, right?
Correct.
Okay. As by the way, Kamal gave said too much, too many good things about me. I am not. I do not know whether I'm worth all that. Anyway, first of all, I want to start my presentation with showing respect to my professors at B College as well as Georgia Tech. In B College, I still remember and check Durga Banerjee, who was our head of the department and then became principal, and then Professor Bhupal Datta, and of course, Professor Amitabh Ghosh or Amitabh Oda, who is still active. And in Georgia Tech, of course, Dr. Novak Zuber. After I finished my master's degree in 71, I was looking for a topic for PhD. And I asked other professors, and they said, okay, you go to Dr. Zuber, Novak Zuber, and he has lots of nice problems of fluid flow, heat transfer, two-phase flow, etc. So I went to see Dr. Zuber and I expressed my interest to work with him. He said, okay, but I have to see whether you are good enough. If I want to work with him, that does not mean that he will accept me as a student. So I said, all right. That time I had to give my presentation of master's thesis, not a defense, but a presentation. So I said, okay, please come. Okay, so he came with two postdocs. One is very famous name, Dr. Ishii, Mamoru Ishii. He is also a authority of two-phase flow, and another gentleman, Dr. Guno, he passed away. He used to be in University of Milwaukee, I think. And another French researchers, Jean-Marc Delahaye, very big names of all this. So they came forth and listened to my presentation. And next day, when I went to his office, he said, okay, all right, I can take you. So that was the story how I got to Dr. Zuber's, becoming Dr. Zuber's student. Anyway, so today I will talk about nuclear power, which I have been working on this for last almost 50 years. And its role, you have heard now last 10, 15 years, and this year particularly, with Europe and also North America going through a tremendous heat wave. The question is, why is this global warming and climate change? And of course, there are experts, some experts who do not believe it, but most of the scientific community do believe in global warming and the cause of it and how nuclear power can help. Okay, so that is the topic of my lecture today. Okay, so the outline is that, yeah, as I said, why we are experiencing this global warming. And then I will touch upon that various energy sources that we have in the world and what is used for electricity generation. Then how electricity generated from nuclear energy, just a little bit basic things about fission, which is the main the way that we harness nuclear energy now. And then we'll talk about a little bit most common types of nuclear reactor today, normal operation, safety system, accident management, etc. And I will also touch upon what India, what kind of reactors India use and the reason, there are good reasons. And then a few words about the use. I prefer to say used fuel rather than waste management. And I will mention why it is called used fuel, just like used car. Used car is still useful. Okay, and then future direction and some concluding remarks. All right. Okay, so this is the picture, and this is from a international body, Intergovernmental Panel climate change, and pretty recent. See, the same thing the scientists do believe, and I'm not really climate scientist, but this is from open literature, that it could be heat wave, just like, even France or Europe and America, North America, had pretty large and very tremendous heat. We are used to heat or summer, hot summer in India, but many people in the Western countries, they are not used to, and they are surprised. At the same time, sometimes there is also flooding, and just I think few weeks ago, Kentucky experienced a lot of flooding, and scientists believe everything is all together. Basically, it is not one thing. Okay, so the question is why. Okay, here is one example I got from NASA. The yellow line is the solar irradiance, means how much energy or solar radiation falls on Earth, and red line is the global temperature. And it's, of course, very, if you see the scale on the right hand side, it's a very small scale, but still, if you see from around 1970 or round about that, the red line is going upwards continuously, whereas the yellow line, which is the solar irradiance, is not going up. It is not because of solar irradiation is high. That is why we are having higher temperatures. So it is not that. So there must be other reasons. And I think if you have heard Professor Amitabh Ghosh in his first lecture of this series, he did show that whenever industrial activity increases, there is, of course, growth in economy and etc. And after Second World War II in 60s and 70s, many countries became independent, like India, China, and many other countries. And the global industrial activity increased. And I think this red line shows some correspondence with that. Okay. All right. The reason is, at least this is the most of the scientists do believe this, that this greenhouse gas concentration is increasing because of burning fossil fuel. Fossil fuel meaning coal, oil, gas, even natural gas, although natural gas is better than coal. And also deforestation because of civilization. Actually, in the rural area where I live, earlier, there used to be many, many trees in many places, and then suddenly, because people are coming to North Carolina from, California, and they have lots of money. The people in California, they come to North Carolina and get big palatial houses. So the builders, they basically get rid of the forest or the trees, and they build apartment complex and big buildings, etc. So all these things are causing increase in greenhouse gas. Left-hand side of this figure is showing that, you see, as the solar radiation comes to Earth, some of it is reflected back. And if everything would have reflected back, then Earth would have been very, very cold, not habitable. Whereas too much of greenhouse gas, which is the right-hand side, shows, which kind of traps this radiative energy, which cannot escape that much, so that increases the global temperature. Very little, but even very little increases. Now we know that a lot of icebergs and everything in the North Pole as well as South Pole, Antarctica, is melting, which is not a good thing, because then the sea level, ocean level may go up a little bit here and there, and the low-lying countries like Bangladesh and many other countries may be in trouble, maybe may go underwater. But so we should do something about it. And the main thing is, main thing is to reduce these greenhouse gas effects. Now, what are these greenhouse gas mainly? It is carbon dioxide, but carbon dioxide is probably the most benign out of all these gases that is shown here. So carbon dioxide, if carbon dioxide is unit 1, then methane, contribution of methane, which is the this place, which is like 25 times. So a lot of carbon dioxide is equivalent to some methane, okay, here. And then nitrous oxide, which comes out from the car, basically for petroleum gasoline burnt engines, that also contribute. And then the fluorinated gases, which now I think the freon industry, they have got rid of that, or at least reducing it. So these are the gases, particularly carbon dioxide, methane, nitrous oxide, that is creating these greenhouse gases. So our attempt has to be to reduce emission or release of these gases, all right? Okay, here I wanted to show that what is the world's energy consumption by sources. And this is pretty recent data. This is from, I think, yeah, goes up to 2020. So that's pretty recent. And here you can see oil or petroleum, coal, and gas, natural gas. They basically contribute. They constitute more than 80% of the energy that the world uses, all countries together. And the other things like nuclear, hydro, wind, solar, and biofuel, renewable, etc., forms only 20%. And so, and burning of this oil, coal, and gas also to some extent causes this release of the greenhouse gases. So it is not just the electricity generation for everything. Say, I think Pankaj a few lectures ago mentioned about how the car efficiencies is being improved so that less greenhouse gas is emitted from the cars. Okay, this is another data or the figure. This is again from the open literature. It shows that death rate and greenhouse gas emission per terawatt hour. Tera is higher than giga, mega, giga, tera. Okay, 10 to the power 3. It goes up. So you can see here nuclear energy, wind, solar, and hydropower. These are really the preferred source of energy for all activities, not just electricity generation, but also transportation and other industrial uses. As you go to oil and coal, you can see that it not only increases the greenhouse gas, which is this right-hand column, right-hand side of the graph, but also the death rate. People do have a fear about nuclear power, and I'm not diminishing that, and I will discuss it towards the end of my lecture. But the main thing is that it is a fact that the death from nuclear power accidents is so minimal that, say, in Japan, when the Fukushima happened 10 years ago or so, and I used to be at GE at that time, 30,000 people died because of tsunami, and only maybe one or two person from in the plant really died because of the accident. It was a great economic disaster, obviously, and a lot of people had to be evacuated, and then slowly, only now they are returning. At least some of them are returning. So I'm not diminishing the negative side of it, but we have to manage it, and that's what I will talk about today. So this is the story or the message from this slide is that nuclear, wind, hydro, solar, etc. These are good sources from the point of view of greenhouse gas emission and global warming. Okay, this is a little bit busy slide. I wanted to show, this is from USA, and it's very recent, 2021. Left-hand side is showing the source of energy. See, petroleum, natural gas, renewable energy, coal, and nuclear. And C, and this side is the end use sector, transportation, industry, residential, etc. And electric power is here because electricity, the whole problem is that only 35% of the energy is ultimately transferred to electricity, and the others are waste through condensers and other things. Anyway, so main thing is that petroleum, see, some goes for transportation, most of it goes for transportation. There are other sectors also uses petroleum. Same is natural gas, same is renewable, same is coal, not in transportation, but other things. But nuclear is basically 100% is only for electricity generation. That is at this time. So it is important to see how we can reduce the use of these fossil fuels, these two and coal, fossil fuels for other sectors also. Okay, and now we are slowly moving to electricity generation. This is again the worldwide energy source and pretty recent, 2021. Here you see again worldwide coal, natural gas, and oil, they are about 60%. Okay, and the good sources, which does not produce greenhouse gas, nuclear, hydro, wind, solar, and other renewables, they are constituting around only 38 or 40% now. So our idea would be to increase the use of these energies for electricity generation, because even if you go for electric vehicle, it needs electricity. And if that electricity is produced by burning coal, doesn't help much. So the source, I mean, the electricity generation should also be as much as possible through these kind of cleaner sources. And that is the direction that the world is taking. Okay, now let me come to actually nuclear power, because that is really the main topic of this discussion. The question is, how do we get heat from nuclear reaction? And then, of course, we use that heat to generate steam and then run steam turbine, just like coal-fired plant. Okay, so here there are two methods, two ways. One is fission, which is currently used. Here there are uranium-235 and plutonium-239. These are called fissile material. So it is only these material, and here example is U-235, that is the most common one. Suppose it is hit by a neutron, and then it fragments into two lighter elements and few other neutrons. Then again, one of these neutrons then hits to another U-235, and then the chain reaction goes. So it is a controlled method of basically building a reactor, nuclear reactor. Okay. The other one is fusion, which is still under development, where we take the heavier isotope of hydrogen and tritium, and then they fuse together, and then they also produce energy. But as you said, this is under development. And here I found a nice short video from open literature. So I would like to share this with my friends here. Just bear with me. There may be a little bit of, I have to. Okay. Okay. These are all, ads. Just bear with me for a keypad. Yeah. Okay. This is what I wanted to show.
So the video is not coming to us.
But your video is running in some other window.
Yeah. Can you not see it?
No, we can't.
Oh. I don't know what to do with it. Anyway, can you see the screen?
Yes, sir.
Yes, the slide is coming. The same slide,
Sir, please escape.
fission and fusion.
Please escape. Print.
What, escape?
Yes.
Yes,
Now?
Escape the screen, sir. So come to the screen and then press escape. Then
Just a moment. Yeah, I'm in the screen and escape. I pressed escape.
full screen
no,
mode.
same full screen is showing now.
It's not working.
Yeah, now it has gone,
No.
but yours sharing has been closed.
Okay. I think.
So you have to reshare.
Yeah. Let me. Oh. This is what happens when,
You can resort to the same set of sequences, going for sharing your screen.
yeah. I'm trying to find out how to share my screen. I cannot see that.
Okay.
Other-
So the
Can you take control?
the
Is it?
Costco WebEx, I think if you look at the bottom
Yes, you should
bottom
find a
part, you
share
should find
button.
your Cisco WebEx.
Sorry,
You are on a wrong window, I suppose.
I'm in the wrong window.
Just try to find out the WebEx window where you could see. Are you able to see all of us?
No,
Okay,
I
so
can see only
that means
mine.
you are on a wrong window. So your WebEx window is minimized. So please find at the bottom the WebEx sign.
Let me get rid of this then. Let me get.
Or you could minimize the other windows to find out the WebEx window.
I know I'm in the full screen. Let me escape from there.
Yes.
Okay. Now, now should I? Okay.
So
Now I got back. Is this the
you see the
WebEx
WebEx?
window?
Yeah, the WebEx. You can probably see all of us, right, on your screen.
I can see. Well, I
Yes.
can see, but I see.
Not probably.
No. Can I? Should I try this again or what?
No, it's
You have to just-
running. The WebEx is still running
WebEx is
because
there, so
you
you
are
just have to
connected.
share.
But the point is you are not able to go to the right window. You try to find out the WebEx window first. The WebEx must be minimized at the bottom. So at the
Okay.
bottom, try to find out the WebEx symbol and open that window.
Is this the one? This is now I can see all of you.
Yes,
Yes,
if you are
there
able
already,
to
so
see
yeah.
all of us, you are in the right window.
Okay.
Okay,
Then
so
click on
so
share.
now you can go for sharing and the same set of sequences.
Oh, okay. Let's see where is the share again. Oh, what is that? Oh, share, yeah.
Yeah.
Okay.
That same window, that window has come, but not the yes. If you now click the video, we can
Let's see.
try to see if the video comes up here or
Yeah.
not.
This is. Sorry, these are.
No, these are the usual hiccups we face.
Now what?
No, the have you run the video? No video is coming. We can
Yeah,
see
I'm running the video.
Okay, that video
Let-
is not coming.
Let's forget it.
Yes,
I
yes.
think you got the message. The students got the message that fission is when a larger atom, fissile atom, is split into smaller one and heat is released. Fusion is when smaller atom like hydrogen atom, they are fused together. And then, of course, the energy release in fusion is much, much more, but it is still under development. Okay. So let's get out of this.
Yeah, if you want to continue from here, you can go back to full screen mode.
Yeah, I think so. I think let's do that. Let me go to the full screen mode. Do I do that again?
So kindly go to the view in the left upper corner. The PDF.
Or if it helps, shall I share the screen?
No. You close the sharing.
I think.
Yeah, it's coming. It's
Yes.
coming.
Okay.
It is coming.
I think.
Yeah.
View.
View
Yes.
full screen.
View.
View. You are within the edit.
Not here. I mean, the next.
Okay.
Not in edit. The next one. View.
Go to the top.
Next one.
Click view.
Yes. No full screen.
Yes. Proceed, please.
I have to stop the other one.
We're not seeing it, doesn't matter. You continue.
If your running video is disturbing you, you can go to that window and close it.
Where is?
Other option is that Vidyut, you can take over.
Yes, I think I should probably share the screen.
Yeah, I think you start sharing it. Pradip, you keep talking. And when you need the next slide, just tell Vidyut next slide.
Okay. Go ahead.
Then do
From
you
this
want
side,
to show
we
the
will let
video also?
Vidyut share.
Sorry for the loss of time also.
Do you want to show the video also?
No, more video. Video is
More
not
video.
necessary.
Okay, then so I will just simply share that.
Okay.
Are you there?
Yeah, I'm just done. Do you see it?
Yes.
No.
Is it visible?
Correct. I can see it.
There may be on the other window. There is not able to see the screen of this WebEx.
Maybe you have to come back to your WebEx screen.
Other application you using camera.
You should be within the WebEx. If you are not within the WebEx, you won't be able to see the presentation.
I'm trying to click open WebEx on the prompt.
No, I think it's already open there. So you just have to find that already open one.
Exactly.
It
It is already there.
somewhere on your.
Yeah, this is the one. Okay.
Yeah.
Now you can take the control.
Yes. So you just tell me when I need to move next.
You move.
Okay.
Okay. I want to make it a full screen so that I can see better.
It's full screen.
We are seeing full screen.
Oh,
You
okay.
just continue.
All right. Okay. So last slide, I showed that for the fissile material, basically when fission occurs when a neutron collide with or and absorbed by a larger nucleus of fissile atom, like uranium-235. And then that nucleus breaks to a smaller nuclei and heat is liberated, and two or three fast neutrons means with high energy, are produced, and the chain reaction continues when at least one neutron again collides with the fissile atom. And there are, of course, range of fission products are produced. These two humps shows most probable fission products. All right, next slide. Yeah. Now, there is something called moderator and also something called control rods to control these fission reactors. Moderator is very, very important because the neutrons that generate are of high energy. They have to be slowed down or thermalized to really react with, again, the fissile material. And that is the moderator. And control rod usually made of boron, lot of borons stuck in there, because boron is a neutron absorbing material. Because if you want to stop nuclear reaction, you insert the control rods so that chain reaction stops. Okay. And most common moderator is either light water, which is used in the boiling water reactor, pressurized water reactor, I'll talk about it, or heavy water, which is used in the Canadian as well as Indian reactors, PHWR, pressurized heavy water reactor. Okay, so usually light water or heavy water. And depending on what moderator you use, you have to enrich the natural uranium. By the way, natural uranium contains only 0.7% of U-235, which is the fissile material. So for light water, it needs a little bit of enrichment of 3 to 5%. Means that portion of U-235 has to be increased to 3 to 5%. Rest can be U-238. Whereas for the Canadian or the Indian PHWRs, the heavy water is used to moderate as well as to cool. There, the heavy water is more, I would say, better to slow down the neutrons. So even though there is smaller amount of U-235, like as I said, 0.7% in natural uranium, it is sufficient to continue the chain reaction. And these are the two type of moderators that are used in today's reactors. Okay, next slide, please. All right. So I'll first talk about pressurized water reactor because that is the maximum, about 300 reactors in the world. USA predominantly Westinghouse started, Westinghouse Combustion Engineering and Babcock and Wilcox. They started this in 60s, and then the French had collaboration with Westinghouse. The French also did. Russia developed again independently. Then China, South Korea, they are basically all followed more or less Westinghouse design. And India also recently, not recently, maybe 10 years ago, they had in Soviet or Russian collaboration, there's already two Kudankulam reactors in the southern tip of India, and they produce their pressurized water reactor. So I guess in India, you have to learn all kinds of reactors. BWR, which is still, which is the oldest one, GE's Tarapur reactor, and then newest is the Kudankulam. And in between, Indian-made pressurized heavy water reactor, like the Canadian reactor. Okay, now here, as I said, the light water, moderated and cooled, you need 3 to 5% enrichment. And this pressurized water reactor is indirect cycle, because this is the reactor, and inside the reactor, bulk boiling does not happen, but it is at a much higher pressure compared to the steam generator or this tube. Steam generator is at 1000 psi, which is about 7 megapascal, and the main reactor is at 15.5. So its saturation temperature is much higher compared to at 7 megapascal, which is 286 degrees C. So the steam is actually produced at 1000 psi, or in America we still use psi and all that thing. Anyway, 7 megapascal, and it goes to the turbine. Okay, this is an indirect cycle. And this is a typical PWR fuel bundle, basically a cross square array, and mostly again, USA, France, China, South Korea, they all use it. Now Russians, they develop a slightly different, this is a hexagonal matrix. This is VVER, and I'm sure that is what is in Kudankulam. Okay, this is the PWR. Next slide, please. Okay, this is the BWR, again developed more or less at the same time in late 50s, early 60s. GE was the main proponent or developer of this reactor. Here, see, this is the feed water. They go directly into the reactor, and actually bulk boiling happens inside the reactor. This is the fuel bundle, GE's BWR fuel bundle. And there is a steam separator and everything here. So saturated stream again at the same 1000 psi. They somehow like 1000 psi. Anyway, goes through the turbine. Okay, so this is a direct cycle, and this also needs 3 to 5% enrichment, mostly in USA, Japan, and as I said, very first two reactors in Tarapur, and it's still working. It was commissioned in 1969, so it is 50 years, still working. Okay, next slide, please. Yeah, this is the CANDU or Canadian reactor. In general, it's called pressurized heavy water reactor. And there are 47, and many of them in India, about 18 or 20. Okay, here, the reactor is horizontal, basically. There are pressure tubes, and this is a big calandria where the heavy water resides, and fluid is also heavy water. I mean, the coolant is also heavy water. And it uses, as I mentioned before, because heavy water is a much better moderator of slowing down the neutrons. This natural uranium containing only 0.7% 235 is good enough. So good thing here is that the people or the countries who uses PHWR does not need an enrichment plant, but they have to produce heavy water. This is not light water, heavy water, and India has it. Actually, I visited one plant in Baroda, heavy water. And it has also advantage of online refueling. Basically, from one side, you push the fuel, of course, very, very slowly, and another side you discharge. And this is a typical kind of fuel bundle stacked one after another. Okay, next slide. All right. Other reactors, there are only few left. Gas-cooled reactor, the British or the UK developed it, and now it's being phased out. They're also going to PWR. And light water cooled graphite moderator reactor, this was developed in Russia, and unfortunately, Chernobyl was one of this type. Now, of course, Russia is not building this kind of reactor anymore, but they're still operating it. Whereas Ukraine stopped after Chernobyl, and Ukraine has only PWRs or VVER, which is a Russian reactor. So both of them are kind of going out. Then another phase, the next phase is the liquid metal, particularly sodium liquid metal fast breeder reactor, LMFBR. Now, two medium-sized reactors are operating in Russia, but no other country has any large LMFBR operating now, but in the past they had. France had Phoenix, Super Phoenix, and America also had, India had. Now India is building one prototype fast breeder reactor, PFBR, but I think as per the latest report, it's still not commissioned. Okay. So this advantage is that generates fissile materials, so transform U-238 to fissile plutonium-239. But there are a lot of controversy about fast breeder reactors because of reprocessing and diverting plutonium for other purposes, not so good purposes. So there is a lot of controversy on that, and the world is a bit slow on this. But this may have a potential for to the used fuel or waste disposal, as we were talking about. Okay, next slide, please. Okay, so now this is again a very, very latest figure. Here it shows how many reactors different countries are operating at this time, and right-hand side showed how much power is being generated. Now, scale is different. USA is a lot higher compared to next one is China and France, but the scale here is broken, okay? But main thing I'm trying to show that USA with 93 reactors operating is producing about 20% of electricity need of USA. France, naturally smaller country, 56 reactors, but producing 70% of electricity from nuclear. China is the country who is building many, many large reactors today, and they have 52 operating reactors, but only catering 5% of electricity because of large country and large demand. Same thing to some extent is India. India has got 21 reactors, operating reactors, but Indian reactors are of smaller sizes, like 200 megawatt, 500 megawatt, maybe 700. Now Kudankulam is 900 megawatt electric. So India also being a large country, even though they have 21 reactors, but the electricity generation is only around 3-4%. All right. So this shows that. Okay, next slide, please. All right, now let me move a little bit to the cooling part of the reactor, because that is very, very important. One colleague at GE told me once, was a nuclear physicist. He said, Pradip, we can generate as much as heat you want, but you guys, thermal hydraulics people, you have to take that heat out of the reactor, otherwise reactor will melt. I said, yeah. So it is the thermal hydraulics which limits the operation of reactors at steady state. Okay, here is a very famous picture of a boiling channel. This is from John Collier's book. Here, suppose subcooled water enters, and this is, say, the passage in that control rods, fuel rods, not control, fuel rods. So in the beginning, it is, of course, subcooled water. It starts boiling, and then, it goes to different flow regimes, annular flow regime, and finally, it's the dry out situation. Now, for PWR and PHWR, usually the heat fluxes are higher compared to BWR. So it is a departure from nuclear boiling, which is the controlling factor, meaning when the bubbles start to be formed at the heated wall, if it coalesces, then there will be a vapor blanketing, and so the wall temperature will go up, like here. But this is more like a BWR situation where heat fluxes are a little bit lower. So boiling can take place, and the quality usually is, say, 15% or so, but void fraction is, of course, much higher. So there are two different criteria for PWR and PHWR. It is departure from nuclear boiling, which happens in this region. And for BWR, it is a dry out or boiling transition here. Okay. All right. So these two are the limiting things for two different type of reactors. The next slide, please. Okay. This is taken from my friend at MIT, his lecture notes. Anyway, with permission, so don't worry. So here it is, as I was saying, say this is the subcooled water is going, and then this is where the vapor blanketing may take place, and so the wall temperature will go up. This is the fluid temperature, and this is the wall temperature. And we do not want that, because if wall temperature goes up, then this sheath or these are zirconium tubes, basically that can melt and the fission products will come out and the accident will start. So basically what they do, the vendors, fuel vendors, they usually run tests, electrically simulated tests, not nuclear tests, but electrically simulated tests of the bundles to find out what is the heat flux for departure of nuclear boiling, that is the limit. And the actual heat flux, suppose it's like this. So as long as it does not touch, that figure is fine. And usually they keep some margin. Okay, that is for PWR and PSWR. The next one will show the similar situation for BWR. Next slide. Yeah, there again, this is basically GE developed this. For BWR, we call it critical quality at dry out or boiling transition. That again, there also actually I even witnessed some tests in San Jose in mid-70s when we were running a full bundle test. Suppose from that, we develop correlation for critical quality. And then we suppose this is the actual quality as you go up the power. And when it touches this critical quality, which is obtained from experiment, we stop. Again, I'm sure we keep some margin. So that determines the up to what power you can operate for boiling water reactor. Okay, next slide. All right, so that was kind of steady state, and also the control. One thing I should mention, there is a beautiful thing in water reactor, which is called void reactivity. Basically, what it means that if power goes up, then the void fraction goes up, and that reduces the moderation, so that reduces the chain reaction. So there is an inherent safety feature in boiling as well as pressurized water reactor, that if void appears, that means power is high, more void appears, then power goes down because of neutronic feedback. So that's a good thing. Then, of course, there are control rods. And usually operators don't want to move control rods too much because that affects the operation. So they would like to do it through void quality relationship or boron, that is for PWR. They have borated water also used. So that is for the standard operation. Now then the question is, suppose there is something is going wrong and they push all the control rods in and everything, reactor is shut down. See, one advantage of fossil fuel plants is coal-fired plants. If something goes wrong, you just stop the coal supply and slowly the furnace comes down. Okay, but here problem is, even if we push all the control rods and we call it shutdown, there is still, you remember, there's a fission product, all those smaller things that was generated, that had some heat and that starts to decay. Fission products start to decay. And here is this is the typical graph in percentage of full power. And for a say 1,000 megawatt electric plant, the reactor power is about 3,000 because we are using saturated steam. So the plant efficiency is around 33 to 35%. Okay, it is a little bit less compared to fossil fuel because fossil fuel probably 40% efficiency. Anyway, but the main thing is that even after time after shutdown, here it is time after shutdown, there is still power, say after 1 minute, something like 3%, after 1 hour, something like 1.5%, and even after 1 day, it could be 0.05 or so. So for a very large, say 3,000 megawatt thermal reactor, even after some time, even so 1% is 30 megawatt. That's a lot of heat. So that is why all nuclear plants have something called safety system or emergency core cooling system. Anyway, more details you can find. I'm not trying to sell my book, but this book has got history of nuclear reactor thermal hydraulics. Next slide, please. Okay, this is the typical for PWR. Okay, this is, as I said, all nuclear reactors are equipped with emergency core cooling system. And I must say this story. When I first joined GE Nuclear in San Jose in June of 1974, my engineering manager, Dr. Gary Dix, gave me a YOLO covered GE report. And very first paragraph of that report had two acronyms which stayed with my life. Like, first one is LOCA. LOCA means loss of coolant accident. And second one is ECCS, emergency core cooling system. So throughout my life, 45 years or so, I'm basically working on the safety system of nuclear plants. Anyway, so here, after this is a PWR, for the core, again, to flood the core, there is, of course, auxiliary pumps. Same thing for the containment, because containment houses the reactor and steam generator, pressurizer, everything. There is also that. Now, all these things do need, for active safety system, it needs electric power or diesel generator. Unfortunately, and same thing is true, next slide, same thing is true for boiling water reactor. Next slide, please. Okay, same thing. Basically, we inject water, and also, of course, boiling water reactor has got the wet dry well, basically a wet suppression pool, which India also took for PHWR. From Narora on, India took this design of pressure suppression pool, which reduces the volume of the containment, big containment. Anyway, so here are, you see, in Fukushima, that's really happened. It's very, very unfortunate. It was beyond design basis accident. Okay, Fukushima had everything, but the tsunami, it is not the earthquake. The plant withstood the earthquake, the pipes were not broken, nothing like that. But the problem was that as per the utility vendor, which is TEPCO means Tokyo Electric Power Company, they said that, okay, maximum tsunami possible is 15 feet from their 200-year data. However, the tsunami in 2011 was 45 feet. So all this equipment, emergency equipment, diesel generator, etc., was maybe slightly above 15 feet level, but the tsunami was 45 feet and it flooded everything and nothing was working. So it is not the country or it is not the type of reactor. Anything, if something happens, this is kind of God, act of God. So nobody can do it. Even I would say, because our people, GE people, were there for refueling, and they felt, and we felt from the other stories, that Japanese operators did the best they could. All right, next slide. Okay, now in 1979, when I was at Brookhaven, basically the first major nuclear accident happened in 3 Mile Island 2 in Pennsylvania. And there, again, it was a Babcock and Wilcox plant. Plant had no problem, but there was a human error and there was some valve was closed. They did not understand. And the pressurizer, PORV, pilot operated valve was open. So it was basically a small break local. And the operator did not understand. So they tried trial and error. And by that time, half the core was melted. So after that, 1979, both the big reactor vendors, Westinghouse and GE, they started developing safety system of passive design. So this is an example. This is Westinghouse, of course, AP1000, and GE is ESBWR. ESBWR is economic and simplified volume water reactor. And this is a picture from open literature again, from a paper by Dr. Schultz. And here the whole idea is to have a lot of water at a higher elevation. And if something happens, you just put the water by gravity down. Even for the containment, they had a system where the outside air could come and go up. It reminded me of our Mahal of Jaipur. Anyway, and these 4 reactors, 4 AP1000 reactors are already operating in China, and 2 are under construction in Georgia, state of Georgia in USA. Next slide, please. Okay, and this is the GE's version. As I said, economic and simplified boiling water reactor. This is the natural circulation BWR. Here, there is no pump, no big pump to pump water through the downcomer and through the sphere. It's all happening in natural circulation. And this is the only equation I have in my slide, which is the velocity, inlet velocity depends on the density difference between here and the downcomer. Downcomer is all water, and this is two-phase mixture. Of course, there's a density difference, and that causes a kind of a gravity head. And the length, this is the length, length also contributes. That's why all natural circulation reactors are tall. And F is the friction, because you have to overcome the frictional head, and we try to minimize the friction. Friction means from here, wherever there are friction, we try to minimize that. And that maximizes the velocity. And I worked on this reactor for 4 years, full time, and I'm very proud of it because it's a very, very good reactor, no question. And the right-hand side shows the safety system. Again, here, just like AP1000, there's a tank of water here, tank of water above the containment, and of course, pressure suppression pool. Everything is passive. There is no pump is not needed. Okay, so electricity is not needed. Okay, and now this, by the way, now one thing US NRC, US Nuclear Regulatory Commission did, because earlier in 70s and 80s, when the plant was being built, they would review the design and all that, then they will ask for changes, retrofit, and retrofitting is very expensive. That is why some reactors took a lot of time and a lot of cost overrun. Now, to avoid that, lately, I mean, not lately, means 20 years ago, NRC decided that, okay, reactor vendors, you can submit your design, we will review it. And once we certify the design, if an utility builds a plant according to that design, we will not question anymore. So questioning part will be before the plant, construction. So AP1000 got certification. ESBWR also got certification. But I would say that mostly because of commercial reason, no plant of this design is being built as of now. May change later, I don't know. Okay, next slide. Okay, now we are coming towards the end. Now, what about used fuel? People usually say, oh, well, this is a waste, nuclear waste is a big problem, and we do not know what to do with this and all that. Now, the fact is that fuel, a new fuel bundle, produces electricity for about 4 to 6 years. Actually, it is taken out from one place of the core to another place every 18 or 24 months, depending on the reactor physics design. So basically, it is usually 3 cycles. So usually at the most 6 years, if it is to a 2-year cycle, then 3 will be 6 years, it is used. And after that, it is not producing energy or enough energy to justify. So they take it out and keep it in a, which is called spent fuel pool. And it is really the used fuel, keep it for some years, and then they can move it to dry cast. Because there has been a debate in most of the nuclear countries, the countries who use nuclear power, what to do with it. Now in America, they had a plan to keep all this used fuel in Yucca Mountain in Nevada, in some place. Okay, and then the idea was they keep it there, and then after many years or so, many years, when more technology, newer technology develops, they can take that fuel out and probably reuse it in another breeder reactor or another reactor. But because of political thing, that is more or less stopped. But some countries, I think Scandinavian countries, they have decided on a geological repository where they will. Here in the USA, there's always problem because if they will say, oh no, why in my backyard you guys are enjoying nuclear electricity, say in Pennsylvania, but you want to bury your bad things in Nevada or Texas. So there is no consensus. And so Obama administration had a blue ribbon commission to see this, and all these big professors and came and went together. But again, there was no consensus. Finally, they said, okay, keep it in the dry cask storage because then the radioactivity level will go down slowly. And then when the new technology comes, then we will see. So basically, they just push the can or kick the can down the road. No consensus in the final disposition. Now, one option is, of course, to use a breeder reactor to produce more electricity. But as I said, breeder reactor is also there is issue with the plutonium, or burying it permanently in a stable repository. So this philosophy or the policy will depend on country to country. All right, next slide. Probably this is my last slide. Okay. So what I feel, and I think most of the technical community feel, that we must keep nuclear energy as an option. Okay, as I said earlier, okay, nuclear, hydro, solar, and wind. These are definitely can produce electricity without generating greenhouse gas. So from that point of view, and as I said before, that 10% of world's electricity is being used to nuclear. So there is no reason why not increase it more. Of course, we're taking safety in consideration. Nuclear industry is serious about now they are going away from large reactor, although as I said, China, India, Russia, they're still building large reactors, even USA. But now for the last 10 years or so, there has been a new move towards small and modular reactor. And of course, I was a little bit, and they were asking for government money. I said, oh, look, we started to develop large reactors from small reactors. Now we are going back to smaller reactors and we still need government subsidy. Anyway, that's a different issue. So I have a friend, NewScale. He's a chief scientist for NewScale, and they have developed a reactor. It's a pressurized water reactor, but natural circulation. So naturally, this is a very tall thing, and core is right here, and steam generator is here. But they're talking about only 50 megawatt electric module, and they're talking about 12 such modules to generate sizable, 600 megawatt electric. And still, they're talking with various people, and whether there will be anything built or not, I don't know. But it is being certified by US NRC. I think it has certified just now. Now, GE also, what they did, I told you about the ESBWR. That was, of course, 1300 or 1400 megawatt electric. So they have also scaled it down to, say, about 300 megawatt. And they're trying to have partners to build such things, but not yet. So this is what I think. And I think that basically concludes my presentation. And this is just, I'm not trying to sell book because I do not get even 1 penny, because this is, GE has given it to ASME. So ASME keeps the profit. But if anybody wants to read, again, I cannot upload it for free because that was the copyright agreement with ASME and GE. Only GE employee can get it. But it's not very expensive. I do not know. Some of you may or may not have. So if anybody wants to know the history and the present situation and future direction of thermal hydraulics or nuclear reactors. This may be a source. Okay, thank you very much. Sorry, I took a little bit of more time because of the mishap with this video business. Okay, I'm through. Now we can start question answers.
Thank you, Pradip, for the wonderful presentation. Now the session is open for question and answer. Please start your queries to Dr. Pradip Saha. We are open. Please start.
Kamal,
I think, okay, go ahead. Ochudha.
Kamal, would you
Yeah,
permit me to start?
Oh, sure. You are always the
First one.
what do we call it? Jogger Hota. You are the person who always does it. Please do
Thank
it.
you. So whatever I say now is my personal opinion and which has been gathered from the science knowledge available in the world. So first thing is we have in the nuclear option a sword hanging over us. There are 444 nuclear reactors in the world today. And since they are all man-made, there are every chance of some accident happening. As we have seen in the Chernobyl, in the Fukushima, and 3 Mile Island. But these are the major which the world came to know. But in every week almost, in one or other nuclear reactor, there is some minor accidents going on. That's it. So the
I
things
disagree.
can.
I disagree. Anyway,
Okay,
go
okay,
ahead.
please. So the thing is, and one more thing I'll say regarding spent fuel, the world does not know what to do with it. Nothing can be done. Only thing is, as a mental happiness, you can put from here to there. That's all. But you don't know what to do with it. And you wait for 1,000 years for new technology to develop to use it. Anyway, those are the other things. So what I suggest now, that we are using motor car, there may be 500,000 human death per year. So once we know the risk factor, there is no way we have to agree to use nuclear power plant as a source of our power, but we must also appreciate that there will be accidents. I'll say will be, since this is a man-made product, there will be some nook and corner, something which has been left, like Fukushima. Who have thought of water 42 high? So such things will happen continuously, but there is a risk factor. Since if we depend on the others kind of power generation, there is not enough metal in the world to permit this wind power and all these things. The metal will get used away earlier than that. So we have to depend maybe on the nuclear, but we'll know that once in a while there will be accidents, and maybe from 1 lakh. There has been a great study on that Chernobyl. Chernobyl was it's a first thing, it is in Soviet Union, so all the American people will throw up on it. They had done great wrong, and there was a great study. Study was done in New York, really. So that says that till date about some people have died in the flu area, but there will be a death of about 1 million people in future.
1 million? No.
Yeah. Okay.
No.
Sir, I said, this is
No,
my
no, I don't
opinion,
know.
and I study a lot. You are a man who knows. I don't know, but I study. So that's my opinion. You have got a liberty to differ. That's it. That's our world. That's democratic world. So there has been a study. It's a published study. It's a 5-volume book which says ultimately there will be 1 million deaths due to this Chernobyl. And so there will be in Fukushima. So there will be in 3 Mile Island. So any new accident, such figures will come out. But we have to study. We have to have our energy. So this is the risk. We take risk in driving a car. We have to take risk in operating a atomic power plant.
Okay.
And fusion.
Can I respond to this first?
One more
Hey,
thing. Fusion is dangerous. You didn't know as yet. I mean,
Kamal.
fission we know. Fusion, I don't know what will happen next. Anyway, I have ended my statement. Thank you very much. But it was a
Can I
beautiful.
respond to Ochuda first? Okay, then Ashok
Kam-
Da can ask his question.
Kamal,
First of all,
Kamal, I like to answer Ochuda's issues. There are answers to it that every week there
Oh,
is
but,
some.
hold on for a second. This is Subhendu,
Yes.
also from our batch, Pradeep and our batchmate. Okay, go ahead to
Great,
comment
great.
on
What
Uchita.
what I was trying to point out here is the work culture and the operational culture is extremely important, is just as important as safety analysis. Now, in USA, since 79 with the 3 Mile Island, then since then there is no accident because the operators qualification, operator retraining program has been revamped to the point it's unbelievable scale. And they maintain a very disciplined work culture. That's operation, maintenance, and everything. And it's amazing how the plant, American nuclear plant, runs completely from one outage to the other outage, the 18 months without tripping. That's enviable. So my answer to Uchuda, your concern is yes, I also read all those little incidents in the Indian nuclear plants, but I doubted the qualification program and the work culture of the Indian nuclear operating plants. And I have also some direct experience with dealing with these nuclear plants in India. So, those things have to improve. And then you probably will get a little comfortable. No, probably a million people won't die.
okay.
That's
For
Cool.
last 20
done.
for last 20
Pradeep.
years, there has been not a single nuclear plant built in America. That
Okay.
shows their safety precautions.
Oh, okay. Can I respond
Yeah,
to
Pradeep,
Ochuda?
Pradeep, now
Okay.
it's your turn. Yes.
First of all, 3 Mile Island accident, we all know, not a single person died. Not a single person or population did not have more cancer or anything. And it has been now more than 40 years. Okay. Fukushima, as I said, this is a act of God because if TEPCO would have told GE that tsunami could be 45 feet or 50 feet, then the plant would have been situated at a higher level. But TEPCO told GE 15 feet is the maximum. So, because there is always a cost involved, as you know, as engineering, nothing is, we cannot build something for millions of dollars, which can be built in 10,000. So there is a cost involved. So the design criteria that was given to GE, because these were GE plants, by the way, and later Toshiba and Hitachi also partnered with GE. So they built it such that the emergency equipment was, I do not know exactly, maybe 15 or 20 feet level, whereas the tsunami was. So that is what we call it. It's a beyond design accident. Now, Russia, China, again, I am not bad mouthing Soviet Union, but this is from our MIT experts, because I was there for 2.5 years. MIT experts that particular design of Chernobyl, and also still it is 10 or 12 is operating in Russia, but Russia is not building anymore. Russia is also building only VVER, which is the pressurized water. Anyway, that particular design has a defect that if the voids go up, power also goes up. That's number one. Second is they were trying to run some weird test to see if you could use a braking thing of some generator or something with turning off the safety system. This is exactly which was done in Bhopal. That is why we had the Bhopal accident. if you dismantle or bypass the safety system and then try to do something stupid, then it will happen. So the whole point is that that particular reactor has had inherent fault, which of course Soviet Union will not admit, but it is the IAEA bodies and others, they went there and studied it, and they said that there was a defect in the design, nuclear physics point of view, and also the testing was being conducted with safety system off, which is just not possible. As Shubhendu mentioned, from 79 onwards, there has not been any, maybe there are minor incidents, but not major accident here. And even in India, I know, say Tarapur is derated because of leaky fuel. Tarapur was originally 190 megawatt electric, but they run it at 150. Same thing happened in Madras too. There were some issues. I cannot discuss it here, but so they basically run it at a lower power. So all countries do take a cost benefit analysis. Say France, for example, France had no coal, nothing. So in early 70s, when the OPEC people cartel the oil supply, France rightfully decided to go for nuclear. And France did not have any accident. They are operating 50 plus big PWRs for now 40, 50 years. So it is the culture, what Shubhendu said. And I'm not demeaning anybody or any country. And all countries who are using nuclear power must have very, very trained technical people. Okay. So
thank you. Discussion will go. We may revisit it, but let me check a couple of quick things before I go. I think Gautam is here. Gautam, are you still here?
Yes,
Gautam.
I'm here.
Okay, Gautam. Do you have any questions or comment from based on your background on fluid?
Ashok has some.
Here. Ashok, you want to ask something?
Professor Saha, this is Gautam from IIT Kanpur.
Okay, yeah, go ahead. Yes.
I am just, it's a, you can say, passive remark. First of all, the lecture was exceedingly well. You covered almost everything related to nuclear power. Some controversial issues are there associated with it. Nobody can avoid it. I'm not taking any side. I'm just only, with this wonderful lecture, there cannot be any, sort of question. I'm just flagging off one small point that since you were in India and you started a company, so probably you are aware of some of the developments. India has entered the third stage of nuclear program. So now what is being attempted is a breeder reactor converting thorium-232 to uranium-233. And
I'm aware of it. I'm aware of it.
And energy released is by the fission of U-233. And it is probably technology-wise much safer. And you mentioned about the fast breeder reactor. With my association with BRC, whatever little heat and mass transfer related problems we get from there, a fast breeder reactor working on plutonium-239 with a capacity of 40 megawatt thermal and 13.2 megawatt of electrical. The reactor is cooled by liquid sodium and uses plutonium, uranium carbide fuel. It is being operated up to, or it has been, I should say, operated up to 18 megawatt thermal and 2.5 megawatt electrical. Operation-wise, it is quite successful, and since safety issues were being raised, it is quite safe. And you have mentioned about the reactor which is being built. That is, of course, a very large, initiative. But many of the things are classified information, cannot be discussed. And probably it will come in 23, 24, depending on the present government's nuclear policy. And but government is encouraging thorium-232 reactors. That is probably a little addition I can, or information I can add to your wonderful talk.
I'm aware of India's effort to convert thorium 232 to uranium-233. Yes, I'm aware of it. But the point is the second phase, which is the prototype fast breeder reactor for 70 megawatt electric. Actually, I met a gentleman, Dr. Chelapandi, I think. He was probably head of IGCA.
Yeah, he's retired.
Right. I met him in Durgapur in one of the conferences, and that was 2013. And he was hopeful that it will come online in 2014 or 15. But I do not know, for whatever reason, it has not. And you see, there is this nuclear news which is being published by American Nuclear Society, and every March they have a world thing about a nuclear reactor in the whole world. And it is written here that for India, this is Bharatiya Novikya Vidyut Nigam, PFBR, 470 megawatt electric. It says commercial. They're expecting this. They have said it October of this year. I do not know. But you
No, that all the things you read October 24.
All right. What I'm saying is what is reported in this.
No, I'm saying that all those are delayed because of several other reasons.
Yeah.
So expected in 24. I mean, I'm just maybe a little proactive thinking or hopeful thinking, because they are going quite slow now.
Thank you, Gautam. Ashokda, you have any question, comment, suggestion?
I have one question, means one query. Pradip, if fusion technology ever becomes feasible, will that be completely safe?
that reminds me of something.
Not in our lifetime.
I was at MIT from 2003 to 5 in the nuclear engineering department. There the standard joke was fusion is 30 years from today.
Right.
Okay.
It is permanently 30 years.
Always 30
Yes.
years from today. But now I think a lot of efforts are going on, and this is of course international effort. Now they are saying, I think very recent nuclear news says that they are hopeful that in another 10, 15 years, maybe something.
So it has reduced from 30 to 15.
30 to
like
15.
I defined old age, a person 10 years senior to me. That is the definition of an old person.
Right.
Thank you, Ashokda. Before we go further, I have a quick question. Dr. Bandapata from Trivandrum, ISRO. Dr. Gigi, you want to make any comment or suggestion? Okay, let's move ahead. Shamol, you are still here? Okay, he's from Japan.
Yes, I am
So,
Bandhavadai
okay.
here.
I don't think he's.
Thanks for the nice lecture.
No, he had a
Informative lecture I could hear.
Yeah, Shamol is our friend also. Same Shamol Kaur. That's what you mean, right, Kamal?
Yeah. That's what I meant.
Shamal told us, we have a WhatsApp group. Shamal told us that during Fukushima or during that earthquake, he was in an office in a tall building and he thought that will be the end of his life. But he survived. Earthquake was huge, no question. But the buildings and other things which were designed, including the nuclear reactors, they survived. It was the tsunami which really killed things. Anyway.
Yeah. Is there any questions from the faculty or the students, please? This is an interesting discussion, and I think a lot of questions are there. Please go ahead.
One quick, just real fast comment on that. On LMFBR, gentleman before this, he talked about 2024, LMFBR coming in India. There is a reason why LMFBR did not flourish in USA. And that was because US's first nuclear ship was LMFBR design. And then during maintenance in Michigan, the sodium got contact with water, and that's extremely corrosive, extremely corrosive. And there was a very bad accident, and a couple of people died. And U.S. scrapped LMFBR nuclear program right there. I worked in Clinch River Breeder Reactor project. That was back in 70s. That was the LMFBR back in the heydays of everything going to nuclear. 3 months after I started working for the CRBRP, and I was told you might find another job because this project is going to be shelved because NRC pretty much told you have to come up with a real good reason why you want to do LMFBR with liquid metal with the sodium, because that's corrosion. It is virtually impossible at some point to avoid. So it just a cautionary note.
If I may ask, what is the prospect of molten salt fast breeder reactor? Because in that case, they say there won't be any fuel rod. You might have fuel even in the mix mode within the salt as oxides form. So,
I don't know all the mechanics of thing. Only I know that how liquid metal fast breeder reactor did not get a slot in the U.S. Nuclear industry. And only
he's talking about a different reactor. He's talking about a molten salt. Now, this
molten salt, people are not talking about molten salt.
Molten salt.
Talking about molten salt, right? Dr. Sudeep?
Yes.
You are talking about molten salt. Yes, this
molten
is a
salt.
concept.
And now they are saying in molten salt.
No. Let me say they are, because again, a gentleman in MIT is the kind of a mover of this, because they are saying that it can reach temperature even higher than the sodium cooled LMFBR. So, and they are of course showing reasons why it is superior to LMFBR. So you see, in USA there are now, even just a few days ago, President Biden signed an agreement or signed a law where a lot of money will be given for nuclear energy as a part of this climate change, global warming issue. So now universities are all going for that money.
Oh yeah, everybody will make money.
Yeah. I survived 2.5 years from the research money at MIT. So what I'm saying, that this molten salt reactor is also a concept, and that is getting some traction. But we have to see when it will can become commercialized. The whole question is from concept to research to a small prototype. That's one thing. And then to go to the real meaningful power. I personally feel new scale is too small, but then my friend, they want to push 50 megawatt, 6 of them, or no, not 6, 12 of them to make it 600.
Yeah.
So I do not know what will happen, but this is one of the concepts that some people are pushing. Yeah.
Any other questions or comments? Anybody? Okay, go ahead, please.
Yes, perhaps not. I mean, not so success of the LMFBR is probably propelling the development of this molten salt, because essentially molten salt is also fast breeding reactor. But you will have the fuel mix even inside your salt. You might have your fuel mix within the salt mix. That's what they are proposing. I'm not sure about the detail of the technology.
Another concept. And
Yes.
this molten salt business was at Oak Ridge National Lab long time ago in 60s. And so Dr. Forsberg, I think he just basically trying to revive it. And he may be successful, I don't know.
Well,
Palit, you have a question? Yeah, you are. Please unmute yourself. Please unmute. You are muted.
Yeah, let it continue.
Dr. Shah,
And,
it was very educative to listen to your lecture. And I had one question which has already been asked by Ashok, that is between fusion and fission. My next question is, it is not a question, it is inviting your comment. Because you have been with Hitachi, G Hitachi. So presently, how is that collaboration going on? We come to know so much about GE, but what about GE Hitachi? For example, they were backpedaling in UK.
Let me answer that.
Yeah.
Actually, GE Nuclear moved their headquarters from San Jose, California to Wilmington, North Carolina in 2003, so 20 years ago. And then you see, GE had Toshiba and Hitachi as their partner in BWR in Japan. You know, some of these Fukushima plants or Japanese plants were built by either Toshiba or Hitachi with GE's license. Okay, so now Toshiba went and bought Westinghouse. I do not know whether you know that.
Yeah.
And then GE then formed, invited Hitachi, and Hitachi, I'm sure, paid some money, some share. And so it became, GE Nuclear became GE Hitachi Nuclear, I think 2007 or 8, I do not remember.
Approximately that time, yeah.
Yeah, correct. And that is continuing. Now, what happened to a big G problem? Big G problem, again, I do not want to badmouth anybody, but the well-known Jack Welch, who was considered to be one of the top management gurus of the world.
Yes, yes.
I mean, he wanted GE to be really at the forefront, and so GE Capital was a big thing. And then in 2007-8, when there was a financial meltdown in USA, GE Capital was in really bad situation. So slowly GE divested GE Capital, but whatever reason I do not know. But fortunately, I retired before all this thing happened. Jeff Immelt, who was successor to Jack Welch, had to resign, and some other people took over, and they just could not. That big conglomerate was very difficult to manage. So recently, they have already announced that GE will split into three separate businesses. One will be GE Power or GE Energy, and nuclear will be part of that. And then the second one will be GE Aviation, because jet engine is a very big and successful business of GE. I think in the world now, all the big jet engines that Boeing and Airbus they buy are a lot of from GE. So that's a very good business. And another is the GE healthcare business, which produces CT scanner and all these other things, MRI machines and things. So these three will become three separate businesses. But nuclear is there under GE Energy or GE Power.
Okay, thank you. Here's the question, Pradip, from your brother.
Oh, from my brother?
Yeah.
Okay,
Pranab, you unmute yourself. and you can ask your question or comment.
And you can show your face also.
Yeah, please, Pranav.
No, can you hear me?
Yes, yes.
Okay, I just wanted to say what I have heard. Very interesting. Very interesting. Laura and I, we are waiting when it will be actually posted in the YouTube so we can take the time to listen to it better. And I'm sorry the video did not work, but that's the way things are. So the other, very good. Thank you.
Okay, thank you. By the way, let me add, I mean, I'm not pushing my brother. He can stand on his own. He's also very successful. He is an acoustics and vibration noise control person. He has also written a book, and he's also B College alumni. So it's up to the Centenary
Yes.
Lecture Committee.
Thank you, Pradip.
Whether
You
want
actually
to hear.
stole.
You heard Pankaj da about.
I will reach out to him.
Past,
Yeah.
but if you want to
Thank
know
you,
about
Pradip.
it,
You stole my words.
Yeah.
Actually, I was going to say the same thing to Bidut. If you want to arrange something on acoustic, he's the guy.
Right.
Okay? He's a big
Today
college guy.
is
I will give
Saha,
the
Pradip Saha's day, and I just wanted
Yeah.
to say it was very good.
Yeah, thank you. Is there any other questions or comments? Please.
Kamal, Pranav
Just
here.
say goodbye.
Go ahead.
Bye.
Is there any other
What should
question,
the-
comment from anyone?
Kamal, Pranav speaking. Can you hear me?
Pranav, okay, go ahead. This is another 68 batch.
Oh,
We
Pranav
are
Rai,
jamming
our
the whole.
friend.
We are jamming the whole electronics. Okay, Pranav Rai from 68. Go ahead, Pranav.
Pradip, I have a very silly question.
Yeah.
Can you hear me, Pradip?
Yes, I can hear you. And no question is silly.
See, nuclear science, as you know, it goes over my head, top of my head, miles above. But I have this small observation, getting to read articles, this and that. What is the final solution for disposal of waste?
Okay.
Yeah.
Say the word waste. He don't like
That's a
it.
very good,
He say-
very good
use-
question. Let me answer. Although the last slide had that one is option is to, of course, burn it in a breeder reactor. And actually, this is again open knowledge. Nobody other than Bill Gates is funding a company called Terra Power. And one of my MIT colleague is there. What they are trying to do is that they will not take any fuel out. They will burn and breed, or breed and burn in the same reactor for 40 years. Of course, they will reshuffle the assemblies, but that is one thing that Bill Gates is funding, and he's, he will not put his money unless he believes in it. It may take time, but I know a group in Terra Power, that's the name of the company, Terra Power is working on it. So that's one option. Another option, most passive option, is to bury it, and that is what the Yucca Mountain was. But then now Yucca Mountain, I don't think will be revived. There are a lot of opposition from Nevada. That same attitude that you guys will enjoy nuclear power and you want to put the dirty
Dump it
stuff in my land. So different countries has got different
No, but I had a wild thought. Pradip, I had a wild thought. Wild. WILD in capital.
Yeah.
Can the spent fuel be loaded onto a intraterrestrial rocket and taken out to outer space?
Those are some of these ideas we heard before, but the question is, what happens if that thing falls somewhere?
Hey, I said outer space.
Yeah. Okay.
Okay.
You can
Is
fail
there
during
any-
launch also.
Is there any other questions or comments or suggestion? I'm asking particularly the students and any questions. This is an interesting discussion. I'll make my final comments right after that. Any other questions, comment? Dr. Bandapada, Gigi, you are still there? You have any question? You unmute yourself, you can ask. Is there any other questions or comment? Please. Okay.
No question. I attended the
Go ahead.
program and it's very informative. You can. Thank you.
Thank you. Thank you, Gigi. Actually, again, he's from ISRO. And, so I just invited him, a couple of them. And thank you, Gigi, for attending. Coming back, any other questions or comments? I think we're also running out of time. Let me.
In that case, Kamalda, give me the last minute for Thanksgiving.
Sure. Sure.
So if there is no question, then let me take that minute just for Thanksgiving. So on behalf of the Centenary Celebration Committee and on behalf of the department.
Hold on for a second, Shudip. Hold on for a second. Just let me thank Pradip. Thank you, Pradip, very much. The reason I want to thank him particularly, yes, thank you, Achyuta. You always take the lead. Okay, Achyuta started the lead in an interesting discussion, but I really appreciate Pradip. Pradip is, you do not know, I didn't have the time to talk about it. He basically moved away from technology and he's in Vedantic philosophy. It is way over my head, okay? Correct. I know nothing about it. He is there, so it was very difficult for me to bring him in. When I first requested him, he said, no, Kamal, I'm out of it. Finally, he thought about it and he knew I was not happy about it. He understood his friend's pain. He came back and he came back because of his alma mater. And I'm sure Pradip is happy now because he saw Ashokda here, Achyuta here, quite a few people. And, it was a wonderful discussion. I'm not going to ask you any more questions, but thank you again for coming and giving a wonderful, very, very, very illuminating presentation. Even if there is some technical, who cares? Okay,
yeah,
thank you
there's a
so
little bit
much.
of problem with the
Yes,
video.
Shudip, now it is all yours. Thank you.
Maybe someday we'll also hear something about Vedic philosophy from Pradip. Anyway, for now,
I'm a student of Vedantic philosophy. You have Swami Sarva Priyanandaji.
Yes,
he's a master of Vedanta, and he's coming at Raleigh next week. Anyway, go ahead.
yeah. On behalf of the department and on behalf of the Centenary Celebration Committee, I must thank Dr. Pradip Saha for this wonderful lecture today. It was really an illuminating one. And let me also thank today's chair, Professor Kamal Sarkar, for leading the session so nicely, encouraging people to ask questions. And we are really glad from being within the department to see all these, old faces of alumni members, including some new faces today. So we are really, and personally, I am indebted to Kamalda for tagging in so many people from the alumni world. Thank you, Kamalda. Very nice of you. Thank you, Pradipda. So thank you very much, both of you. So with that, we'll be closing the session now. Yeah, it was a long session indeed. We started a little late. So let us stop the session today with thanks to last responsibility. There is a certificate of appreciation which we'll be sending to our speaker. The electronic copy will be sending through email. We do have a hard copy along with a memento which we plan to hand over. The point is, the difficulty is in handing over because so far we have 30 lectures, we could hand over only about 9 or 10. So that problem remains, but still, because we are not giving anything to our speakers, so that's why we are keeping the memento in stock. So memento and the hard copy somehow we'll arrange to hand over either in the country or outside the country through courier or through our personal people. Hand delivery. We'll arrange that. Maybe it will be taking time. So I would seek excuse from our speakers for that. If we are late in delivering it to your doorstep, please don't mind. Someday, somewhere, we'll.
Thank you.